So today I'm going to be talking to you about Monte Carlo simulations of local statistical field theories. Just to give you a very brief outline of my talk, I'm going to begin by giving an introduction to Monte Carlo simulations, and my talk is mainly going to focus on the parallelization of these types of simulations. So what Monte Carlo simulations are is they are a very general class of methods which allow us to study the properties of field theories on computers using numerical methods and random sampling techniques. So I'm going to use the Ising model as a simple example to talk through the nuts and bolts of a typical Monte Carlo simulation. And when I've done that, I'm just going to talk about some of the work that I've did as part of my master's thesis, where I created a generic and a parallel C++ class designed to run these types of simulations in parallel. And this class actually worked for a range of different types of field theories using the same class. And then when I'm done that, I'm just going to finish by talking about some of the things that I'm interested in now, which is numerical methods for Lattice QCD simulations. So again, as I said, the main goal of Monte Carlo simulations really is to study the properties of field theories on computers using numerical techniques and random sampling. And the way these methods work is by discretization of the field theory that you're studying onto the sites of a discrete and a finite lattice, meaning that we restrict the field variables to live at every site of a grid. And these field variables then can take different values depending on the type of field theory that you're studying. And they take a different structure depending on the properties of the field theory in question. And how these simulations typically begin is you start off with some initial configuration of the field theory. So where at every site of the grid, you have a certain value of the field at every point. And what you want to do then is you want to sample a sequence of different configurations of the field. So you want to move from one configuration to the next using standard Monte Carlo techniques such as a metropolis type algorithm. And when you have this sequence of configurations, what this allows you to do is it allows you to sample a region of phase space of the model. And then this region of phase space and all these configurations allow you to compute observables that you're interested in. So some kind of properties of the model. And once you have these properties of the model, they allow you to look at other things such as phase transitions of the model as well. So that was a very general introduction. So I'm actually going to use a practical example, which would be the Ising model. And so the Ising model is probably one of the most well-known examples of these types of statistical mechanics systems. And so in the Ising model, we have degrees of freedoms of plus or minus ones, which we place at every site of the lattice. And so these will be our field variables. And what these plus or minus ones represent is magnetic dipole moments of a collection of interacting atomic spins. And in these types of simulations, what we're interested in is observing how these spins interact with each other and looking at their behavior. And this is actually a very good model of ferromagnetism, because we see that when all the spins are oriented in the same direction, we say that the system is in a magnetic state. But when they behave in a very unorderly fashion, the system is no longer magnetized. And so this is actually a very simplistic way of looking at magnetization, and it's a very well-known model in that sense as well. And so, as I said, the way we run Monte Carlo simulations is by looping through or generating a sequence of configurations of the system. So some orientation of all these spins at every site of the grid. And we do this using the metropolis update. And what the metropolis update does is it moves from one configuration to the next, depending on the energy difference between different configurations. So you can imagine in a practical implementation of this, what we would do is we would loop through every site of the grid, and we would look at the energy of the system, which we obtain through a function known as the Hamiltonian. And then we would propose changing that spin to move to a new configuration. And we would look at the energy of this new system by computing the Hamiltonian again. And then we will move to that new configuration with a certain probability, which is given by this metropolis update here. And so for every site that we visit, we have to compute this Hamiltonian here. And this Hamiltonian actually for the Ising model is made up of two terms. So the first term is like an interaction term. And then the second term is just a term which describes the influence an external magnetic field will have on the properties of the model. And so once we've generated the set of configurations that we're interested in, this allows us then to compute whatever properties we're interested in. So something like the average magnetization of the model, or something like magnetic susceptibility. And we average these observables that we compute at every configuration over the full set of configurations that we generated. And then once we have these observables, we can look at things like phase transitions of the model. So where the model undergoes a phase transition from a ferromagnetic to an anti-ferromagnetic state. And we do that by running simulations at different values of input temperatures of the model here. So that would be this T here in this, this update step. So it's just an example of what some configurations of this model might look like in 2 dimensions and in 3 dimensions as well. And this is a set of configurations that were generated from a sample configuration run. And so what I mainly want to talk about in this talk is the parallelization of these types of simulations. So as I said, when you're either updating from one configuration to the next, or when you're just computing an observable that you're interested in, these simulations work by doing some computation at every site of the grid that you're on. So one way of trying to parallelize these types of simulations is by taking the grid and dividing it up amongst different processors on a computer and assigning a subsection of the grid to every individual processor, so that every processor only owns its own subsection of the grid and only updates its own subsection of the grid. And you can imagine if all the processors do this together simultaneously at the same time, then we can speed up the computation and achieve a much better performance in our simulation runs. But moving these types of simulations to parallel has a few problems. The first problem is typically when we're doing some computation on a lattice site, we require data and information from neighboring lattice sites. So for example, if we were updating this point here on processor 0, this red point, if we were evaluating the Hamiltonian, the first term, which is the interaction term, requires information from this neighboring point here, which is actually owned by a different processor. And so in order to do these types of parallel computations, we actually need to be able to communicate data between processors. So in this case, processor 1, we want to communicate data to processor 0. So processor 0 can actually use the data from that point in its computation. So one thing we need to consider when we're doing these types of simulations in parallel is equip each subgrid of each processor with an additional layer of data to, or additional layer of memory to store the data from neighboring processors. So we want to be able to send and exchange data between processors, and this is typically done in parallel environments through something like MPI. And this type of communicating data between processors is actually is a significant overhead in these types of parallel simulations, which I'm going to talk more about later. One other thing to consider when you're doing these types of updates is when you're updating a particular point, you want to ensure that it obtains the correct bit of data from its nearest neighbor. So since they're all working together simultaneously at the same time, we want this bit of data going to processor 0. We want to ensure that it's the correct one, and that's the old data which we got at the beginning of that time step, and not some newly updated bit of data. So one way of doing that is by coloring the grid so that for every grid site that we have, all of its neighbors are a different color. And so we update only one color at a time so that we can guarantee that the data that it's using from its neighbors have not already been updated. And this ensures that we have no stale points in the evaluation of the Hamiltonian at every step of our simulation. So this kind of motivates me to talk about this motivates the work that I did as part of my master's thesis. And so in my master's thesis, what I did was I created a generic and a parallel C++ class designed to run these types of simulations. And the reason why we want to run these simulations in parallel in the first place is because typically we're interested in running simulations on large lattices. And larger lattices lead to more computations. And so there's a significant amount more work is needed for running these types of larger simulations. But in addition to that, we also have additional storage requirements for storing larger grids. And so, as I said, A solution to this is by dividing the lattice up among processors and doing the computations simultaneously on local subgrids. So why would we want a generic class to do something like this? Because typically we're interested in running simulations of different types of field theories, and different types of field theories have different physical properties which correspond to different field variables. So for example, the field variables in the Ising model, we just had plus or minus ones to represent the different spins. But if we are running simulations of something like a scalar field theory, then we would require the field variable to be more general, and it could take any real value within an interval. And so we would have to use double data precision for something like that. And so the way this class would work then is you create a certain instance of the class depending on the type of field theory you want to study, and you can use any data type you wish depending on how variables at every type of the grid. So the main ingredients to memory to store the grid. But because it's a three-dimensional grid, we can only guarantee that two surfaces will be stored contiguously in memory, meaning that nearby elements will be stored beside each other, whereas for the remainder, this may be fragmented in some way. So I drew kind of a diagram here to illustrate this. So in this diagram, we just take the same grid, but I highlighted a different surface on each copy to kind of highlight where every surface is stored in the memory allocation. And here we see the first two grids are stored contiguously, whereas the remaining four surfaces are the memory is all fragmented in some way. And this leads to problems as well when you're trying to communicate different data between processors, which I'll talk about in the next slide. So we also want an MPI exchange function, and this is the function then that we will use to actually exchange data between neighboring processors. So as I said, because we want to exchange data on every surface, we need to be able to exchange non-contiguous data. So typically when you're exchanging data with MPI assumes that you're exchanging a contiguous string of data, meaning that all data that you're sending is stored contiguously in memory. So in one block of memory, which is all stored side by side for every element. But as we saw on the last slide, for 4 of the surfaces on the grid, we want to exchange data that is not contiguous. So I wanted to test a few different approaches of how we could send this data, and I wanted to choose the best possible approach based on the performance of sending data in that way. So I tried a few ways here, and one of them was looping through blocks of contiguous data and then sending each block separately while skipping over the non-contiguous blocks. But then another approach was just sending all of the elements individually, which led to very poor performance, as you can imagine, because you're doing multiple sends and receives all at once. But the best approach that I found was to use what's called pack and unpack methods. And what these methods are is they're methods which allow us to pack all the data from each surface into one large vector. And so this vector is stored contiguously in memory. We can then send that one contiguous vector to the relevant processor and unpack the data into irrelevant surface locations on the other side. And so this is actually the best approach because it only involves one send and receive, but with the extra cost of the additional expense of these functionality for these pack and unpack methods as well. So how would you actually decompose the grid? There's different things you can consider. The first one I wanted to look at was a stripes decomposition. And the reason why I wanted to look at this type of decomposition is because every processor, the lattice is decomposed in such a way that every processor has only one neighbor in one direction. So it only has one direction of exchange. So left and right, for example. And the advantage of this is that if we decompose the grid in such a way that the left and right neighbors correspond to the contiguous surfaces, then we can avoid the exchange of non-contiguous data. And so we don't require these additional pack and unpack methods. So one good thing about this is there's less communication, so there's less neighbors than other types of decompositions, but at the price of lower grained parallelism in these simulations. So another more general type of decomposition then will be the cubic decomposition. And so what the cubic decomposition is where we partition the lattice more generally so that there is neighbors in every direction. But when you consider a decomposition like this, then you're forced to have to deal with the exchange of non-contiguous data corresponding to the non-contiguous surfaces. And so a decomposition like this would require additional pack and unpack methods in your class to exchange these surfaces. One good thing about this type of decomposition is you get finer grained parallelism in your simulations, but at the expense of more communication, more directions of exchange, and the additional computation of implementing these pack and unpack methods as well. And so what I did in my thesis was I created a class which corresponded to both of these types of decompositions, and I wanted to look at the performance observations for running simulations with these types of decompositions for different lattice sizes. And what I found was both of these decompositions scaled very well. So regardless of the advantages and disadvantages of each, we still benefit from moving these simulations to parallel, despite the excess cost of communications. But what I did find was the cubic decomposition did outperform the striped decomposition for larger lattice sizes, meaning that for the finer grained parallelism became worth the excess cost of the communication and the additional methods for packing and unpacking data. And so this is a simple diagram that I included just to show some simulation results of a test of the Ising model that we did using my class. And the reason why I decided to include the average magnetization as an observable in the simulation was because it gives us a nice way of showing where the phase transition would occur in the Ising model simulation. So for a particular value of beta, which is just our inverse temperature, there's a critical value at around 0.22, and this just represents where the model undergoes a sharp phase transition between ferromagnetic and anti-ferromagnetic states. So I'm just going to talk about what I'm interested in now, which is an extension of these Monte Carlo techniques to deal with more general field theories with more complicated field variables. So what I'm really interested in now at the moment is numerical simulations of quantum chromodynamics, but in particular the numerical methods that we use to study QCD. So what quantum chromodynamics is, it's a quantum field theory, and it describes the interactions between quarks and gluons. And what the theory describes is how these quarks and gluons interact and how they form, how they bind together to form particles which are known as hadrons. So common examples of hadrons would be particles like protons and neutrons, and these are the composite particles which are found inside the nucleus of atoms. And so what QCD is it's a quantum field theory which describes this interaction. And it's actually a very large pillar of the standard model of particle physics. So one interesting thing about QCD is it's a strongly coupled quantum field theory at low energies. So at these low energies is where these hadrons arise. So it's where quarks and gluons bind together to form these hadronic particles. And because it's a strongly coupled quantum field theory in these energies, means that we can't use perturbation theory or perturbation expansions to study QCD at low energies. And so in order to study QCD, we need to use non-perturbative numerical treatments to study the theory at these types of energies. And so we do this using these types of Monte Carlo techniques that I was talking about. And this is a field of study called Lattice QCD. It's where we discretize the field theory onto the sites of a lattice. But in this case, instead of 3 dimensions, the lattice is actually 4-dimensional. So we have a dimension corresponding to time in addition to the 3 spatial dimensions. And so the goal of Lattice QCD really is to compute low energy properties of QCD. So things like masses of hadrons, decay constants, and other interesting parameters of the theory as well. And it's based off the path integral formulation of quantum mechanics, which states that the expected value of some observable that you're interested in can be defined in terms of an integral over all possible configurations of the field variables. And so how QCD works basically is we want to evaluate this integral And we do this by discretizing the theory onto a lattice, and we put the field variables of the theory, which are now, they're no longer plus and minus one spins like the Ising model. Instead, they are quark and gluon fields, which represent the fundamental degrees of freedom in QCD. And so we put the quarks on the lattice, but in addition, we also have gluon fields living at the sites of the lattice as well. And so this transforms an infinite dimensional integral into a finite dimensional integral with a very high number of degrees of freedom when you consider numerical discretizations. And this works very much the same way as what I was talking about in the context of the Ising model, except now we want to evaluate this integral by taking samples of different possible configurations of quark and gluon dynamics. And so there's two main steps of these types of simulations. And the first one is the generation of these types of configurations of quarks and gluons. And the second is the computation of correlation functions, which give us the properties that we're interested in the model. But this is a very large computational task based on the fact that both of these steps require very large and sparse matrix inversion. And the matrix in QCD are incredibly large. They're of the order of hundreds of thousands. And so it's not possible to run these simulations in serial, so we have to run them in parallel, and they're typically run on very powerful supercomputers. And so what I'm particularly interested in now is in the development of numerical methods for solving these large sparse matrix equations that arise in these simulations. And because they take the form of shifted equations, I am typically interested in the development of Bloch-Krylov methods with preconditioning for solving these types of systems. So that concludes my talk. I'm very happy to take any questions that anyone might have. So thank you.